Welcome back. We are at the last portion of chapter 4, and we are going to go and talk about Thevenin and Norton. Before doing that, I want to refresh your memory about what we just talked about an hour ago, and that was about source transformation. I want you to see it in a different light this time. Now, I have a circuit in front of me. I have a voltage source, a current source, I have a bunch of resistors, and this is my point of attention. I want you to consider this as load. So if I consider this as my load, I'm going to go and basically change that in terms of color. So I'm going to remove this. I'm going to stretch this wire. Remember, we said this is going to be a kind of a rubber band. So that was 2 ohm. This is going to be plus minus 0. This I'm going to call RL. RL could be anything, and in this case, 2 ohm would be my RL. This could be my RL, this could be my RL, but let's keep it simple. Now, if I wanted to do source transformation, what am I supposed to do? I can't do anything. 3 and 5 are not in series, neither they are in parallel. I can't do anything in the middle. The middle is actually blocked. All I can do is this, 10 volt and 5 ohm, I need to change that to a current source, because they are in series, to a current source and a resistor in parallel. The resistor is going to be the same, the current source. If I just isolate this segment in my mind, this segment, just isolate this from the rest, and imagine that this point is shorted in your mind, then what kind of a current do you expect? The current is going to go through the plus, through the 5 ohm, through the short, come back, finish the loop. So the current has to go this way, because if I had a short at the end, I expect the same behavior to manifest. How much is the value? 10 volts fall across the 5 ohm, and that would be 2 amp. I can replace this with 2 amp and 5 ohm. There was a reason for this, because if I do, then my hands would be much more open in terms of what can be in parallel and what can be in series. I'm going to go in and I'm going to remove this segment and replace it with this one. So I'm going to have a current source, and then I'm going to have this resistance, which is 5 ohm. Okay. Now I'm conscious. I can see 2 current sources are in parallel. These 2 are in parallel. If I observe this node, $2 comes to my pocket, $4 comes to my pocket, so I need to replace 2 and 4 with a current source that come to my pocket, and you are sitting on this node. So I'm going to replace this 4 and this 2 amps with 1 amp, and I can do that because they are in parallel. So I do pre-check that. Are they in parallel? Yes. Then I go ahead. 4 plus 2, that's going to be 6 amp. I'm a step closer now. This and this cannot interact because they are not in parallel series. But I have the luxury of taking this and changing this to a voltage source and a resistor. So here is going to be a voltage source, and here is going to be a resistor. The resistor is going to be the same. The voltage source. For a moment, isolate this section and have this as open. The current source come in, hits the head of the 5 ohm on the head, creating a plus on top and a minus at the bottom. And 6 times 5 is going to be 30 volts. Okay? Now, I want you to take this structure out of the place and replace it with the transformed structure. So this is going to be 5 ohm again, and you happen to have 30 volts. Now, the end game is obvious. The reason you did this, because you wanted to have 5 and 3 in series, and you are going to put them in one resistance. I'm going to remove this, and I'm going to have this as 5 plus 3 as equal to 8 ohm. let me draw my original design to you. Now I can, of course, I can say what is my VO, and VO is equal to 2 divided by 2 plus 8 times 13. This one is going to be 10, it's going to give me 6, so this is going to be 6 volts. Right? Now I want you to go back to the original design and feel what we did. Of course we utilized the technique called source transformation to achieve that, but in the original format you had the following design in mind. You had a voltage source, you had a resistor, you had a current source, and a resistor, and then you had the load. Okay, now the resistors would be 3 and 5, and the value would be 4 amp and 10 volts. If you look at the process, you can see that through successive change of source transformation from voltage to current and so on, I was able to replace this segment with this segment. The eventual transformation of this block is a voltage source and a resistor in series. I simply showed you how to get a Thevenin. Thevenin is going to be for any given block. Here is my system. This is my block. I don't know what it is inside. I only know that this is linear, and this is going to be my RL. Through whatever technique you have, if you come in and say, I can give you a resistor and a voltage source, then you gave me Thevenin equivalent design. This is called V Thevenin, which happens to be 30 volts. This is called R Thevenin, which happens to be 8 ohm. If you give me that library out of a complex design, you gave me a Thevenin. Similarly, if you have done source transformation or whatever technique that we are going to talk about in a moment, you use whatever technique that it is, and you come in and you say, I'm going to replace this, instead of a voltage source and a resistor in series, I'm going to replace this with a current source and a resistor in parallel. You gave me Norton. This is Norton equivalent design. We already know from the source transformation technique that if I know Thevenin, how do I get my Norton? I'm going to call this I of Norton, and I'm going to call this R of Norton. I'm going to talk about the properties and the way in various environments how to find these equivalent designs. But if you found Thevenin, and most of the time Thevenin is a lot easier. If you find Thevenin, it's very easy to find Norton. Norton is one last source transformation of Thevenin. Thevenin is one last source transformation of Norton. So if you happen to have this and this, actually let me go back and call them accordingly and appropriately. I'm going to call this R Thevenin, and I'm going to call this V Thevenin. If you have this, how do you get this? All you have to do is to copy R Thevenin and put it here. That's your R Norton. And V Thevenin, you can imagine a short in mind, V Thevenin divided by R Thevenin. That's going to be, let me write it down with a different color. V Thevenin divided by R Thevenin, you got it. Rn is equal to R Thevenin. That's exactly what we do in the source transformation scenario. If you happen to know this one, how do you get this one? R Thevenin is equal to R Norton And V Thevenin is equal to I Norton, excuse me, R Norton, I Norton. So, when we ask you to find an equivalent, Thevenin equivalent of a design, we mean that remove everything. Whatever happens inside is none of our business. Remove everything and give us a voltage source and a resistor in series. When we ask you to find a Norton, remove everything and give us one current source and a resistor in parallel. So that's the idea. Let's take a look and see. But you see, sometimes source transformation are possible, such as the example I just showed it to you. Sometimes it is. But most of the time, it's not really possible to do source transformation. So how I can get my final Thevenin Norton equivalent out of a scenario? That's what I'm going to explain now. Okay, let's go back to my Thevenin. I am assuming that through a number of processes, you have been able to replace the design with one resistor and a voltage source in series. And obviously, this is going to be my load. If the load is short, RL is 0. If the load is open, IL is 0. Eventually, in this simple structure, you can see that IL is actually coming from here. IL is eventually coming here. You see, this exists. When you load this IL exists. And as it goes, this is in parallel with this, so I'm going to see this one as V Thevenin. VL, I'm sorry, VL. VL. So if I ask you to write me a KVL law, I need you to write me a KVL law. Let's go back and imagine you have a big loop. Let's start from this end. Minus V Thevenin plus R Thevenin times IL. And then plus VL. That's what VL is. I don't want to put the resistor in picture, as equal to 0. Minus V Thevenin, minus head, and then R Thevenin IL, that's plus minus, and then I have VL, or VL here, as equal to 0. Let's draw this line and see how it looks like. So V Thevenin, I want to take this V Thevenin to the other end. V Thevenin is equal to R Thevenin times IL plus VL. Let's draw this on a 2-axis graph. This is IL and this is VL. This is a line. This is telling me how to find V Thevenin, basically according to various combinations. This is a line. Now, if IL is 0, what happens to my V Thevenin? If IL is 0, this term is gone, and V Thevenin is equal to VL. So this one is going to be V Thevenin, because this is IL 0, this one is IL 0, IL is equal to 0, and that's my V Thevenin. What did I just say? I say that if IL is 0, this is going to be VL and V Thevenin will be the same. If IL is 0, VL and V Thevenin are the same. If IL is 0, I mean this is open. So basically, I'm identifying this node as open voltage. I'm going to leave this open, and whatever VL is, that's my V Thevenin. Let's take a look at this equation one more time, and this time I want you to put VL to 0. If you put VL to 0, how much would be your IL? So if you solve the system for this, you are going to get V Thevenin divided by R Thevenin. That's going to be your IL. The condition though is V Thevenin, VL is 0. What do I mean by VL is 0? We talked about it in the past. When VL is 0, one of the possibilities we have in mind is that RL is 0. RL is 0, you have a short line. So this is a short line. If I want to find IL, all I have to do is to short this and get that. Let me go back, and I want to actually show it to you on the graph for the maximum impact. This is the circuit when I have left it open. Okay. I have left it open. This is open. This voltage is Thevenin when it's open. Here, I have the following scenario. I have this, and then short, and then I have Thevenin. So this is Thevenin, this is Thevenin, and this is IL. So I need you to know what this point is and what this point is. You happen to have two nodes, 2 points of the line. All you have to do is to simply go ahead and connect these 2 nodes. That's a line. It may not look like a line to you, it's a line. This is a line, a linear equation. This line can be identified in 3 different ways. Either you have this point and this point, that's one way. You have this point and this line, the slope of the line. The slope of the line is going to be Thevenin. Or you have this point and the slope of the line. So the 3 techniques I can identify this are follows. I can find Thevenin for IL0, and I can find basically this one. I'm going to say Thevenin divided by Thevenin for VL0. I can find these 2 points, point A and point P. If I find point A and point B, I've got my line. The second technique is you can have point A as point A, and you can also have the slope of the line. I'm going to have this line, and since I know what the slope of the line is, I'll just draw a line. And I'm going to have my line, and all the behavior is going to be captured. So I'm going to have Thevenin, slope. And the third technique is, I'm going to have Thevenin to Thevenin, which means VL is equal to 0. That's node B. That's node B. And then I'm going to have the slope of the line. Okay? You already know through the source transformation that this represents open, IL is equal to 0, and this represents I Norton. This one, when VL is equal to 0, if you, excuse me, if you wanted to replace this with a current source, you would have replaced that with the IN, then you would have a resistor in parallel, and then you would have said, hey, let's put this as a short and see how much this is. This is supposed to be the same as IN. So basically, this one is already IN. Tell me Thevenin, IN, I give you the line. Tell me Thevenin and the slope, I give you the line. Tell me IN and the slope, I give you the line. But there are behavior that are going to help me find this. So let's see. If you happen to have a block, I want to know, I went from a simple model, I went to the equation, I went into the graph, I understood what it is. Let's go back and see what I mean by this. You see, engineers are supposed to actually manifest the understanding in the practical steps. This is a design. I don't know what it is. There are some resistors, some voltage source, some current source, there are so many and something connected. I want to know how I can replace this with the Thevenin. This graph, this equation, that understanding tells me a few things. Leave this open. Leave it open. When you say leave it open, I mean remove this. There is no load. No load. If you get me this voltage when there is no load, you got me a Thevenin. That's very important. That's really important stuff. Which means if I'm giving you a circuit, I want you to remove the load, let it open, tell me how much that voltage is. That's my Thevenin. What is the last point? The last point says this. The last point says, why don't you connect this and tell me how much this current is? This is I short. This is V Thevenin divided by R Thevenin. Tell me how much this current is. Remove the load. Of course, you are not supposed to do that in the lab. You are not supposed to replace the load and replace it with a short wire, because obviously we don't want to burn anything. But just from theoretical point of view, remove the load, give me a short, tell me how much that current is. That's this node. A math understanding now is beginning to manifest itself into a practical step. But I want you to give me a slope. What do I mean by this slope? A slope of the line, R Thevenin, R equivalent. I mean, this is actually a part of a definition. We don't go into more details than this. But the idea is this. And we have learned how to handle this in chapter 2 and 3 and so on. Shut down all the independent source. Independent source. Assuming you don't have dependent source. The actual definition is this. The actual definition is put a voltage source as a test voltage. Make it, for example, 1 volt. Tell me how much this current is. If you tell me that R equivalent is equal to 1 volt divided by IO. This is going to work even if you have dependent source. But since in this class we don't want you to engage with dependent source at this time, there is a simpler idea replacing this definition. The idea is this. Shut down all the independent source. You don't have the independent source. Shut down all the independent source. Look at this angle and tell me how much R equivalent is. You've got so many ways of identifying your Thevenin. You can tell me this, that is open voltage and R equivalent. You can tell me this, that is a short current and R equivalent. You can tell me this and make it and get it done. I'm going to go in and basically give you a number of examples. Actually, from the same example we started, it's a simple one. I'm going to solve that, then I'm going to go and solve 2 more cases so that everybody knows what to do. Same example, please. This example we were able to handle through source transformation, which was an easy technique to do. But I would like to study this through a different light, and that is just the light we explained. The technique we just explained. Okay. Okay. Now, my load is 2 ohm. Let's go back. That's 2 ohm. There is a reason I'm actually drawing this far. Because I want you to be able to distinguish between non-loaded stuff and the loaded stuff. Okay? The question is, give me Thevenin of this. In order to do the Thevenin, well, we can find the Thevenin in 3 different techniques. I'm going to go and actually study the design with 3 different techniques. And each time, you are supposed to get the same response. You are supposed to get the same response. So, Let's remove this. This is my point of load. If I leave this open, whatever voltage I'm going to get, if it is open, it's going to be Thevenin. Let's do that. If this is open, this current, how much that is? This current is 0 because it is open. I said open, and remember please, in Thevenin, the issue is different. When you are facing the design as an open load, it's completely different than finding, for example, R equivalent or anything else. Because, generally speaking, IL is not 0. Generally speaking, IL could be anything. But when I say open, IL is forced to be 0. So that's one thing we have to know. This is 0. When this is 0, the voltage across this is 0. Therefore, VL is actually this voltage. V open or Thevenin, this is going to be actually the same as this because there is no voltage drop. Let's take a look at this one more time. I'm going to remove that for the sake of simplicity. There is no current that goes into the open load. I want to find V open. Because it's only one loop, you can go ahead and have some loop assignment. Let's go clockwise, and this clockwise is actually opposing this. It's going to be minus 4 amp already, so it's going to be minus 10 plus 5 times minus 4 plus V open is equal to 0. So it's minus 10 minus 20 plus V open as equal to 0. And therefore, V open is coming from the rest, not because of the current source. V open is equal to 30. If you go back to your notes, you see that we already found this at 30 volts. This is 30 volts. Okay? What did I do? I left the load open. V open would be my Thevenin. I've got the Thevenin, which is the same as what we got in the superposition, what we got in the source transformation. Let me go back to my original design. Each time you need to be able to move back and forth between different scenarios. That was, I believe, 3 ohm and this. How much is R Thevenin? R Thevenin, if I'm able to find R equivalent, that would be my R Thevenin. In order to find R equivalent, all I need is to shut down these independent sources to 0. When I shut down this to 0, that's a short line. When I shut down this to 0, that's an open line. So let's take a look. It's going to be a short line. Then it's going to be 5 ohm. Then it's going to be open line. I just want to make it very, very small because I don't want that to interfere with your imagination. And then you're going to have 3 ohm. And then here it is. How much it is? You can see 3 plus 5. Is it 3 or 2? Was it 3? That's what's 3. 3 plus 5, that's going to be 8. So I'm going to replace R Thevenin is going to be 3 plus 5 is going to be 8 ohm. If you take a look at what we did in the previous stage, you must have had basically an 8 ohm already. Okay? Thevenin now has been found by open line. R Thevenin now has been found by shutting down the current source and the voltage source. Can I find my I short or I Norton? You see, I'm not worried about R Thevenin because R Thevenin and R Norton are the same. If I wanted to, I can actually have gone through this final source transformation from this stage is going to get me my Norton. You can also find your Norton through the definition. Let's go by definition and see how the Norton is going to play out. It may sound very difficult topic, but as soon as you pick up and you say, I'm going to use mesh, I'm going to use nodal, superposition, whatever technique you have in mind, and I advise against superposition because it means you're supposed to solve the design 2 or 3 times depending on the number of independent sources you have. So please don't go that far. How much is my short? I short. I short is I Norton. How much is that? Well, let's begin. This is a mesh equation. Let's go and have this one. I'm going to call this I alpha. I'm going to call this I beta. I'm touching this current source twice. I'm going to remove one of these guys and replace it with the big one. Okay? And I'm going to call this I theta. The internal loop, it's very easy. This current is actually going to the same direction as 4 amp. I beta is 4 amp. You got it already covered. The only thing that is left is the outer limit. So let's start from this point. It's going to be minus 10 plus. When I get to 5, remember I theta is the master and I beta would be the slave. Or I theta is the leader and I beta would be the follower. So it's going to be 5 times I theta plus 3 ohm. I theta is the leader. I beta is the follower. But the challenge here is this. Are they supporting each other or are they opposing? It's going this way for I theta. It's going this way for I beta. So it's going to be the summation as equal to 0. There's nothing else. You have 3 components and 3 terms. Now I beta is 4. So let's simplify. This is going to be minus 10 plus 5 plus 3 I theta. You have 5 and 3 I theta. And then 3 times 4, that's going to be 12 as equal to 0. Therefore, hopefully everything is fine. And therefore, this is going to be 8 I theta. And this is going to give me 2, goes to the other end. It's going to be minus 2. Okay? But I theta is not my I short. If you take a look at this as a component, as a branch, I short is going this way. I beta is actually supporting it, and I theta is supporting it. So I short is actually equal to I beta plus I theta. I beta is going to be 4, I already know, and I theta is going to be minus 2 divided by 8. Sorry, divided by 8. So this one is going to be 32 minus 2 divided by 8 as equal to 30 divided by 8. That sounds familiar to us. If you remember what I said before, you had 30 volts and you had 8 ohm in your Thevenin. How do you get your Norton? Your Norton is going to be a current source. It's going to be a resistor. The resistor is obviously the same, no change, and the current would be 30 divided by 8. 30 divided by 8, and since this goes this way, it has to go this way. 30 divided by 8. What I try to show you though is this. What if I can't do source transformation? The definition says, if you want to find a Thevenin, you need to find V open and R equivalent. You can find I short and I equivalent, or you can go a long way and find V open and I short. We don't advise V open and I short, which means you're supposed to solve topology, 2 different topologies. That would be a heavy job to do. And it happens only at the time when the circuit cannot be analyzed any other simpler way. I want to solve a complex scenario and then go into the maximum power transfer. Okay. It's page 144. It's an example of the textbook, and in the tutorial part, obviously, we will be doing a number of questions and covering a number of materials. a current source 2 amp, 4 ohm, 12, 8, 5, 'Okay. A and B. Sometimes the question doesn't show the load, assuming that the load will come in and interact with the design. Sometimes it says, here are the two terminals, terminal A and B, and obviously sometime at some point of time and some processes, I'm going to have some RL. The question is, I want to replace this with a Thevenin. Norton is not really a major issue, because as soon as I find a Thevenin, I'm going to do a source transformation, I'm done. So here's the case. Let's remove this. Let's begin. Case number 1 is relatively easy. I want to find R equivalent. How do I find R equivalent? Well, since I have only independent sources, I'm going to shut down the independent sources to 0. Set this to 0, that's an open line. Set this to 0, that's a short line. So what do you get? You get a 4 ohm and a short line. You get an 8 ohm. You get a 5. And then you have your hand on it. Please note, as I said, in Thevenin, you don't know what the load is. The load could be 0. The load could be infinity. The IL is non-zero typically. So this I is not 0 necessarily. You have your hand here. You have your eye here. This is your eye. This is your hand. So I need you to make sure that you know where your hands are. And then you look into the design. With this perspective in mind, you can see 8 and 4 to be in series. That's 12. And then you see 5 in parallel. And the rule of thumb says, let's make it easy, 12 plus 5. So it's going to be 60 divided by 17. Let's simplify. It's going to be 3.53. So my 3.53, my R equivalent, which is going to be my R Thevenin, is already known. And this technique works if I have independent sources only. And if I do have a dependent source, I need to put a test voltage of 1 volt and measure the current. I need to excite the dependent source. We talk about that later. But generally speaking, R Thevenin or R Norton for that matter is already known. Done, finished. Okay. That's going to be 3.53 ohm. How much is this voltage? Well, if I leave this open, all I'm going to see V Thevenin. If I leave this open, I want to see V Thevenin. And V Thevenin is the same as this one. I want to see this. So let's go back in and try to find V Thevenin however you like. Mesh, nodal, whatever you want to do is really your choice. Let's remove this. Okay, I want to remove this for the sake of better visualization. You know what I'm trying to do? I'm trying to find the voltage across the 5 ohm. If I assign this as my reference node, I have a 12 volts. Well, obviously 12 is equal to the plus side minus the minus side. The minus side is 0, therefore this is 12 volts. And apparently all is left for now is to solve this. If I find this voltage, I can find V Thevenin later. So let's call this Vx. Minus 2 is entering. Vx minus 12 divided by 4 is for this. Remember Vx from an imaginary point of view is the biggest voltage of the circuit. Vx minus 0 divided by 8 plus 5. Remember, it's open now. The reason I can say 8 and 5 are in series because I'm talking about open scenario. And that's really different than in a general case. So I need to solve this. This is going to be I'm going to take Vx, 1 over 4, 1 over 13, as equal to 2 plus 12 divided by 4 is 3, so it's going to be 5. Let's solve this. 5 divided by 1 divided by 4 plus 1 divided by 13. With your calculator, don't do any more simplifications that is needed. So here, my Vx is going to be 15.3 volts. But that's not my Thevenin. Vx is 15.3, I need to find Thevenin. If this is 0, if I write the case yellow for this, Thevenin, that's this one. This voltage, the voltage of this node is going to be Thevenin. Thevenin minus Vx divided by 8. Thevenin minus 0 divided by 5 as equal to 0. I'm actually doing a voltage divider. Do you see this in front of me? I see a voltage divider in front of me, and the voltage that is supplied to the voltage divider is 15.3. You can solve this easily. Thevenin, 1 over 8, 1 over 5, as equal to Vx divided by 8. I already know what Vx is, almost 16 volts. That means 2. Well, we utilize the calculator one more time. 15.3 divided by 8 divided by open bracket 1 over 8 plus 1 over 5, and it's 5.88. So Thevenin is 5.88 volt. 5.88 volt. You got yourself a Thevenin. Okay. Apparently, in this structure, I forgot a resistor. A resistor 8 ohm is missing from the example of the book. That's fine, and that's why the answer of the textbook is different, because my topology is different, but that's fine. So what did we do? We shut down the independent sources, we found our equivalent, we left the load open, we found the Thevenin, we are set to go and claim what my Thevenin is. If you know what your Thevenin is, you simply go ahead and you do a Norton. Now the last topic of this chapter would be maximum power transfer. I'm going to erase this and begin the maximum power transfer and talk about it in a moment. Okay? Now there is a reason for the majority of devices that you see that they have a 50 ohm input impedance. Here is my general scenario. That's going to be my Thevenin, and this is going to be my R Thevenin. Of course, we are talking about a DC at this time, and then there is going to be a load. This is going to be RL, this part is going to be VL, and this one is going to be IL. I want you to feel this design, because that's the way you would know why we call it maximum power transfer. Now, if RL is 0, which means this is a short line, which means VL is 0. And of course you can see IL would be maximum. That's when the fuses go up. Why? Because as soon as you put the wires in, and hopefully you don't, please don't, then the maximum current happens and the fuse of the device pop up. So basically, when I have it as a short, my IL would be Thevenin divided by R Thevenin. I know what this name is. This is Norton. When RL is infinity, which means it's open, let me write it down, open and short. When RL is infinity, that is open. Obviously, I expect IL to be 0 because huge impedance in front of me. Nobody can move, right? Now that's what happens to IL. And then take a look at my voltage. Because the IL is 0, the voltage drop across this resistor is 0, and therefore this voltage is the same as this voltage. So VL is equal to Thevenin. That's what we said. That's the definition of Thevenin anyway, right? I want you to plug this on a VL IL scenario. So basically, this is going to be my RL, and this is going to be my VL. And then I use a different color to show what happens when the IL is considered. For VL, if RL is 0, I'm going to have VL 0 and when RL goes to infinity, I'm going to see the maximum possible voltage that comes out of it. So here's the case. That's the way my VL versus RL goes in. Eventually it's going to be stabilized. You can't expect anything more than Thevenin. If Thevenin is 20, you cannot have anything more than 20 on that side. DC, of course, right? If you take a look at the, in blue, I'm going to draw, if you take a look at the current, what happens? When RL is 0, I'm going to have the maximum current. When RL is infinity, I'm going to have the minimum current. This one and this one. Let's plug this. Maximum current, I'm going to write it as the blue. Maximum current, and obviously the maximum current comes in and eventually dies down, goes like this. IL blue and VL red. Okay, let's change this color please. VL. Okay, now tell me about the power that goes to the load. What is power? If you remember the power equation, PL is equal to VL times IL. Okay? Well, tell me what is happening. VL is 0, IL is maximum. What is the PL? PL is 0. VL is 0, IL is maximum, PL is 0. As I can see, PL is actually going up and then coming down. I'm going to show that in black because I don't have any more color left. So as you can see, this is going to be the way my PL is going to manifest. This is PL. The majority of devices we have work with power. When I say I have a bulb that is 60 watts, it's working with watts. It's power, right? So I want to have the maximum power transfer to the load. I don't want to dissipate the power. I paid a lot of, a huge cost for it when I created the power, of course in an AC domain. In Niagara Falls, I went through a huge cost to generate this. Then if I wanted to transfer this to somewhere else, and if I want to lose this energy in between Niagara Falls and Toronto, I'm actually losing money. So I don't want to lose the power. I want to have the maximum power transfer to it. So my question is this: what should RL be to be able to absorb the maximum power? I want this guy to absorb the maximum power. That's the question. So we are going to find, actually there is a very simple formula. I'm going to lay out the proof because eventually you guys need to know the critical thinking behind it. But it's really simple. It's really simple. A bit of a math, but it's really simple. Okay. Tell me how much is your VL. VL, according to the voltage division principle, is RL divided by RL plus R Thevenin times V Thevenin. How much is IL? IL is equal to V Thevenin divided by R Thevenin plus RL. Well, V Thevenin, I have two in series. I'm going to divide it. That's what it is. How much is my PL now? PL is going to be the multiplication of these two. So let's do that. V Thevenin is fixed. I can't do anything about this guy. That is coming from the original source of energy. So V Thevenin is constant. When you multiply this, V Thevenin is going to be V Thevenin to the power of 2. Then I'm going to have RL divided by RL plus R Thevenin to the power of 2. What is changing? RL. What is fixed? R Thevenin. It's not yours. What is fixed? V Thevenin. That's not yours too. Again, this is applicable for the DC, and similar stuff is going to happen when we go into the AC mode after the midterm. But there, we are going to talk about it in a bit more complex scenario rather than just real numbers. Now, how do I find my maximum PL? All I have to do is to say what is the derivative of PL in respect to RL, and I want this to be 0. That's when the maximum happens. So the question is, take a derivative in respect to PL, RL, and put it to 0. You have a fraction, the constant doesn't matter, so the constant comes out and basically is going to move away. So take a look at this. Derivative of the numerator times the denominator minus derivative of the denominator times the numerator. So this one is going to be, this is constant, a scalar, it's coming down. Derivative of this in respect to RL gives me 1 times RL plus R Thevenin to the power of 2 minus derivative of this in respect to RL numerator. But take a look, that's the power of 2. The 2 comes behind. Derivative of inside bracket in respect to RL, that's going to be 1. So it's going to be 1. Then whatever is left inside the bracket, and then of course times the numerator, and of course you have RL plus R Thevenin to the power of 4. That's how the derivative is going to work. Please remember, I have an RL on this. Now I want this to be 0. A same scenario requires me that V Thevenin is a non-zero element. Also, I'm not expecting RL to be negative in this class. RL could be negative in the 4th year class, but not in this class. So because RL is positive and R Thevenin is positive, the summation of the positive, I need to see how it goes. This is not going to be 0 at all. Therefore, I'm not worried about the denominator. That's not the challenge. It's not singularity in one sense. So take a look at mine. Numerator. RL plus R Thevenin to the power of 2 minus 2RL plus R Thevenin times RL. If this is equal to 0, my derivative is going to be 0. Let's factorize RL plus R Thevenin. What is left out of this is RL plus R Thevenin minus 2RL as equal to 0. Again, because RL in this class cannot be negative, or R Thevenin and RL summation cannot be 0, I'm not worried about this bracket. This is the bracket which takes me to my destination, and that is to be 0. So let's take a look. R Thevenin, RL minus 2RL is minus RL as equal to 0. R Thevenin is equal to RL, or RL is equal to R Thevenin. That's the key conclusion. The key conclusion is this. If you want to have the maximum power transfer, RL needs to be R Thevenin. I need these two to be the same. You might be surprised, but as you increase RL, while VL is going up, RL is coming down. As you decrease RL, while basically IL goes up, VL comes down. That's the balance. The balance point would be RL is equal to R Thevenin. What is my power at that time? Well, let's calculate this. This is what is part of the midterm question. So PL is equal to V Thevenin, you have nothing to say. RL is supposed to be R Thevenin. RL is R Thevenin plus R Thevenin to the power of 2. That's how I'm going to simplify. This is going to be 2r Thevenin to the power of 2, 4r Thevenin to the power of 2. So it's going to be v Thevenin to the power of 2, 4r Thevenin to the power of 2. One of them is gone, 4r Thevenin. That's PL maximum. PL maximum. Okay? So when I give you a circuit and I'm asking you to tell me how much RL is going to be for a maximum power transfer, I am implying that please find the Thevenin. And as soon as you find the Thevenin, RL has to be equal to L Thevenin. And as soon as you make that decision, that's going to be your maximum power anyway. With this, we have covered chapter 4. And next session, we are going to go into the tutorial mode. And one of the things that I would like to discuss would be a bridge, and then a number of examples as far as I can go today. And that would be the sessions for us before the midterm. Thank you very much, and talk to you